Springs. Do springs have energy? Potential energy. Could they, Cassia, could they also have kinetic energy? If they're moving, and I don't mean like moving as a whole, or like if they were bouncing, compressing, right? Now, there's also, yes, that's true. Where did that? Oh, where did it go? I just saw it. Oh, here we go. Is this a spring?
Yeah.
Does it have kinetic energy?
Yeah.
Bouncing up and down, right? Now, some springs. Some springs are made. Now, these are the world's worst notes here, right? So springs, you can either you can stretch them, right? Or some springs you can compress. Or some springs will actually go both ways, right? Like this one, sort of in its resting state, is resting compressed, right?
But it doesn't push up.
That's right, it doesn't push up, right? Like it doesn't, like if I put my hand on it, it doesn't push me up, right? Some springs are designed to sort of sit like that. Some are designed like this, like a shock. And some are kind of designed to kind of do both, right? It kind of depends on, like, what would you call that? Like, no, not this. What would you call that property that kind of determines what kind of spring it is? Like some are like squishy and some are stretchy.
Sure, you'll call us.
Oh, I will. What would you call it? It's like a tension, right? Are some springs stronger than others, Josh?
Yeah.
Like if you think about, like, could we, if we wanted to, could we bust this slinky by just like stretching it right up?
Yeah.
Fairly easily, right? Like if Brett and I grab out of there, we could probably pull out, and we wouldn't have a spring where we have a wire. Right? If you take like a little spring, actually, who's got like one, like a kind of a pen, a clicky kind of one? Let's take the spring one. Right? This one. If it doesn't work, then like don't bust it. No, don't. I probably have one.
I don't know what I'm saying.
Here you go. Yeah? Well, don't throw it, 'cause I'll drop it. Oh, excellent. Okay. This is a great spring because this one is designed to be like
Pushing down. You can never.
Like it's expensive, right? And it's designed to do this, right? Is this one stiffer?
Yeah.
It is way stiffer than this one, right? It's got like a little bit more. It's kind of almost like friction, isn't it? Right? Like a frictional coefficient. We can call it the spring coefficient.
Is that right? Yeah.
We could. We could call it spring coefficient, right? Now, Brett, can we stretch this one out to a wire? Absolutely, right? Would it be harder than this one?
Yeah.
Probably. I don't know. It's thinner, right? Yeah. Did I ever show you guys the dropping sling thing? Did I ever show you that video?
No.
Oh, yeah.
You're gonna show us.
The bottom won't move to the top, right?
Yeah.
Did you ever see that?
You won't be able to see that.
Okay. So, this is all related to a guy by the name of Robert Hooke. That's him there. He's a little stoic. That's the way they took pictures back then, right? So Hooke's law relates the amount of force that you exert on a spring to the distance that the spring is either stretched or compressed. Okay, so it's basically how much force you need to stretch a spring. You don't need to write that down. Not worth it. Not worth it. Okay. If you were to graph force versus distance, it would look like that. Because the more you stretch, the more, like, like, think about a spring, right? Anybody ever have one of those? They had these when I was a kid. They have like these two handles with three springs, and they were like a workout thing at home. Anybody ever seen one of those? Yeah. Like at a garage sale or something? The more you pull them apart, the harder and harder it is. Like that last little bit's pretty hard, isn't it? Right? Okay, because the more you pull, this is the force, and this is the distance. The farther apart they are, the more force required, right? So that would be what your graph of force versus distance look like. By the way, when you do the Hooke's law, guess what it's going to look like?
A straight line.
It won't look like that, right? From this straight line graph, we get that F, instead of D, we're going to use X. X for distance. The force is directly proportional to the X, right? And it will lead us to the equation F equals Kx. When you change a proportionality statement into an equal sign, you put a constant of proportionality in it. Remember I talked about at the start, is that there's that certain amount of stiffness in a spring? That's what that K is. Okay, the K is how strong that spring is, and many springs have different strengths, right? Like the shocks on a big giant truck would be much stiffer than, say, the shocks on a little Volkswagen truck, right? I think so anyways, wouldn't they? Yeah, of course they would, right? Okay, so Hooke's law says the force exerted upon a spring is directly proportional to the amount the spring is stretched or compressed. That's the law. I'm not going to ask you to recite it. It's pretty much common sense. It just says the farther you stretch, the more force. That's really what it says. And is Megan writing everything down?
She's writing everything down.
That's a terrible person. You're right, whatever makes you feel comfortable, right? EJ, who are we to judge? Constant of proportionality. The constant K is called, just as we predicted, Johnny, the spring constant. That's what you said, right?
Yeah.
Hang on, that was me that said that.
No, I said it.
You said it too? The constant of proportionality is called the spring constant. And oddly enough, we actually use the letter K. In this particular case, K is the slope of the line. In fact, K is always going to be the slope of the line. In this particular case, the slope was 35. Okay? Force is measured in newtons. Distance is measured in meters. And so we would say the spring constant here is 35 newtons per meter. For every meter that you stretch a spring. Now, who stretches a spring a meter? Nobody, right? You're just going to turn into a wire. But the base unit is the meter, and so that's the spring constant. So it might be like 3.5 newtons per 10 centimeters, right? That is a constant. Now, here's the weird thing. Usually when you guys think about constants, like pi, or what's another constant that we've used in here? 9.8. What's that? Which one?
I don't know.
Friction, right? Frictional coefficients. Could they be more than one number?
Yeah.
They could, right? You could have like wood on wood as 0.2, or maybe tires on rubber road might be 0.5. Frictional coefficients can have different constant values. Springs are the same. They can have many different constants. Okay? The spring constant gives the amount of force required to stretch the spring a distance of 1 meter. But again, the 1 meter length is very rarely actually achieved. Exactly. That's a good word for it. This is fun to play with. I'm just going to do this.
A big slinky at home that makes my hands smell like metal, so don't use it.
It makes your head smell like metal.
Hands.
Oh.
Go on.
Yeah. Okay. Now you have sample questions, right?
Yeah.
So here's the first one. It's sort of embedded within these notes. Okay. Does everyone see the sample questions that I handed out earlier? Okay. So here we have a sample. We've got a 6 kilogram mass attached to a vertical spring. The spring stretches or compresses. It doesn't matter whether you're stretching or compressing. A distance of 40 centimeters. Find the spring constant. Okay, this one's pretty easy. We are solving for. We're solving for K. Pardon me? Doesn't matter, no. So the 40 centimeters we're going to have to convert to meters. That's right. So it's simply, and it's a vertical spring, right? So how much force? We got to convert 6 kilograms. We got to convert that to newtons. 6 times 9.8. 58.8 newtons is required.
This is like the last formula you're going to be teaching us.
It is. It's the last of a lot of things, John.
This is like really strong. Like, I don't want to talk.
Wait, just wait till we get to this one. Then you'll be right.
Trying from like sadness and like just zen.
Who knows? Who knows? Who knows what'll happen in my next?
And
Who knows what'll happen? Anyways, moving on. F equals kx. So what F do I use? 58.8. What do I use for x? 40 centimeters in meters. 147 newton per meter. you tend to get sort of larger numbers because of that meter thing. Okay? So this particular spring, this one only, has its spring constant 147. 58.8 divided by 0.4.
So the X is distance.
The X is distance. I don't know why they use X instead of D. I don't know.
So could we write our formula as
If you want to have it as X, you can, or as D, you can, I guess. I guess that would be F equals KD.
the force of Bastion or
See, maybe that's why we don't use D. Because, yeah, kids get hungry, get distracted.
I can use some tractor.
Someone asks a silly question like, does it matter if it's like spiral KD or something or other, you know?
oh, good one. Doesn't matter if you're spiral. They're all like
Spring
10% crack.
Yeah, is it? Tastes better?
You drop one, lose.
It has to. More pure.
Okay, now, how does work relate to springs? Do I do work when I'm working out with that grandpa workout thing? Am I doing work? Sure am, right? I'm moving in a distance and I'm applying the force. And we know that the last centimeter or two is harder than the first centimeter or two, right? So you're actually doing more work as you get to the end, right? So consider the amount of work that you do on a spring with a 200 Newton per meter constant. This is not an example, right? It's just, well, it is, but it's a theory example, right? Okay, so, what have I got here? Where's delete? Work equals force times distance, right? And the force exerted is found by Hooke's law. And so, in other words, this Kx is going to go in there. Okay? Suppose that this data was found. Okay? As you don't need to write this down. We're just doing a derivation here. Don't write this down. As you're getting a larger and larger distance, the force goes up, right? So we ended up, at the last little bit, we're using 100 newtons of force, and that we've stretched at a distance of 0.5. What's the average force exerted here? If I started at 0, and I ended at 100, I heard someone say it, 50, right, Sierra? Oh, you didn't say it? Christine, was that you? Trying to give you credit, someone over there. Take credit for it, Sierra. Because you're right. You're right, Sierra, 50. Well done. Right? 0 plus 100 divided by 2, 50. So we can take the average, which is 50 here, right, and multiply it by the total distance. Right? How much work did we do? We did 25 Newton meters. We did average force. Average. You guys know that the bar over top means average? Average force times distance, 50 times 0.5. We did 25 Newton meters or 25 joules of work. Where does that work go when I stretch that spring? Where does it go? Because I've done work. It goes into the wire. It's not heat. A little bit, Brett, would be given off as heat, right? But it's all as spring potential energy, because when I let go, it goes back, doesn't it, right? Same thing with Brett's pen. When we click it, we apply a little bit of force, we do a little bit of work to push it down, and then when you let it go, it bounces back, right? If you do it enough, there's probably some heat generated. Okay? Same way with elastic bands. Same way with, anybody ever done bungee jumping?
Yes.
Did you right? No?
Yes.
Same thing, right? A bungee is just a big giant spring. Okay. Now, is there another way to calculate this work done on the spring? And the answer, of course, is yes. Right? Remember, the work done can be found by W equals FD for a constant force. Right?
Is there a spring in mechanical pistons?
No, that's based on friction. It's like a gripper kind of thing like this, and when you push it, it opens, and it pushes it down, and then you let go, it clamps it in place. So it basically pushes it out and then holds it, right? Pushes it out and holds. Kind of like a one-way lock, yeah, exactly. Or those finger handcuff thingies, right?
Chinese handcuffs.
Yeah, is that what they're called? Yeah.
But I always
Yeah.
want to.
If we had a constant force, if we had a constant force like this, well, what would F times D be equal to? Right? F times D is work, but if it was a constant force, then that would also be the area, the area under that graph, would it not? So what if we don't have a constant force? What if we've got one like this? Like, what would this graph look like?
And we can plot it and make it into triangle.
Yep.
Oh.
On a force distance graph, what is the area equal to?
The work.
Work. Right? On a force distance graph, the area is work. I'll say it again. On a force distance graph, the area is work. I'm saying it again because these are cues you're going to have to pick up on your own next year. Because they're not going to say, I'm repeating it because. They're going to, emphasize somehow, maybe a little bit louder, maybe wave their arms around. You might just have to recognize it on your own. On a force distance graph, the area is work. Okay? So the area under would be, right. So the area under our spring graph.
Johnny.
Yeah. Okay? So here it is again, FD, this area is the work. Well, look at this graph. The area is 1/2 the base times the height. When we did our average force, didn't we go 0 plus 100 divided by 2 is 50? Like, isn't average the same as kind of finding the area, like half the base? There's that half thing again, right?
Question number?
Right? So it's half the base, half times 0.5 times 100, or if you want, 100 times 0.5, half of 100 times the 0.5, again, 25 joules. Okay. So what I'm saying here is, key point, area of a force distance graph is the work. Algebraically. Blah, 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 blah. Let's go through this. Area is half the base times the height. Area is half the distance, that's the base, times the force exerted. But the force exerted by Hooke's law is kx, Johnny. So I put kx in for force, and now if I use x for distance, now I've got 2 x's, right? So the area is 1/2 kx squared, and that, my friends, is known as the potential spring energy. US equals 1/2 kx squared. US, potential spring energy. US, it's the potential energy in a spring. The amount of potential energy in a spring is equal to 1/2 K, which is known as the spring constant. X.
But X is distance, right?
X is distance here. Why, Brett, you say we use U because, I guess you could go PS, I guess, right? Potential energy spring.
Well, I've been using E3.
Oh, yeah.
It's still on.
It'd be EPS then, I guess, wouldn't it, right?
Potential spring energy equals the area.
It is area, but this is the formula that we're going to use, right? It's the area. I'm just showing you that the formula, US equals 1/2 kx squared, the formula actually comes from the idea that the area is the work. That's what I'm saying. I'm sensing that there's another sample question here on the next page. Do you get the same feeling? Feels like we've sort of reached a marker. Bingo. Bingo. Was the dog's name all? In all the years I've been fostering, I haven't had a dog named Bingo yet. Maybe next. You know what I should have been doing all these years? Is I should have been getting dogs' names from students as suggestions. Because they have, Danielle, you know, you've done some volunteering in the Humane Society. They've got some really weird dog names out there. Right? We should come up with like a list of like potential dog names. Shaq. Marley. Actually, I think we had a Marley dog. Oh, yeah. Max is, I had a Max in my house. Max ended up with Mr. Burnat's brother, and then Okay, here's a sample. If you do 24 joules of work in compressing a spring whose constant is 80 newtons per meter, how far is the spring compressed? So we are solving for, how far we are solving for? X, right? We are solving for X. So we're going to write US equals 1/2 kx squared. Where does the 24 joules of work go? It goes into the spring. So 24 is our potential energy. 1/2 kx squared. 80 is the spring constant. We're solving for X. You should get X is equal to 0.77.
So, with potential spring energy is just work.
All of the work done goes into the spring. Okay, now, serious question. Anyone done bungee jumping ever? Okay. One of the first things they do is they weigh you. Why? Well, if you're bigger, if you weigh more, you're going to.
Oh,
Why do you stretch it more? More force, right? More force is going to stretch it farther. So, like, who's been to the what's it called there, in Edmonton? West Edmonton Mall. Anybody been there?
Yeah.
And they got the wave pool.
Yeah,
And,
that's
and they,
cool.
you can bungee jump from the top.
Yeah.
Not for me. Right? Oh, really? They were bungee jumping when I was there. I didn't even like watch it. But anyways, okay. So let's talk about bungee jump for a second here. Where would you climb up? Let's say you climb up like 200 meters. 200, let's do this. Right? 200 meters, and you jump off. Where does the energy, where does the work come from? Like, what stretches the spring?
Your weight.
The force of gravity, your weight. But initially, like, let's say at this point up here, let's say you've got, we'll just make it a round figure, let's say you've got 1,000 joules of gravitational potential energy. Right? If you were to stretch all the way, and let's say that they've got water down here, if you were to stretch all the way in your bungee right to there, when you're at the surface, the water level, you would have how much potential energy? 0. So where does 1,000 have to go? Into the spring, doesn't it, right? So they need to know exactly how much you weigh, and they know how high they are. Basically, they're figuring out the 1,000 joules because they want to know how far you're going to stretch that spring. And if you're a bigger person, well, you're going to need one with a bigger coefficient or a smaller coefficient? Bigger, like a stiffer one, right? Exactly. Because they don't want you to. Bad for business. Bad for business. Oh, this must be sample number 3. Yeah. This spring? They would not go all the way to the bottom. They would well, no, they would fall, but they would like go and they would be like hanging and they'd be like bouncing way above the water. How do they get you back up?
There's a crank.
There's a crank. Yeah. And then once eventually it's all stretched out, then it becomes a rope, right? Yeah. Or maybe they lower you. I don't know how to. Yeah.
That'll be scary.
Okay, let's do this one. Is it sample number 3 on yours too?
Yeah.
Okay. So a spring, 200 newtons per meter, has been compressed 0.1 meters. So it's already been compressed. This one's a little bit different. Already been compressed. How much work must you do from this point to compress it to the point 4? Hang on there, Ty. I know you're falling asleep. I can see it. Just hang in there, brother. Okay, so let's stop and think here. So it's already at point 1. It's got to stretch it to point 4. How much farther do I have to stretch it?
3 more meters?
How much farther? It's at point 1. I got to stretch it to point 4. It's got to go 0.3 more, right? So can I just use 0.3 in my formula? Why not, right? Like, is it going to be the same amount of work going from 0 to 0.3 as it is going from 0.1 to 0.4? It's going to be the same distance, but is it going to be the same amount of work? Why would it be harder, Brett? Because you're going to need more force at that end,
Oh,
right?
gross.
Right. So what are you going to have to do?
I don't know.
Well, the work done, remember work done is always transfer of energy. The work done is the spring energy gained, right? So we have to find USI and USF. It's easy. USI is initial spring energy. USF would be final spring energy. Would they both be the same formula? Yes, same formula, 1/2 kx squared. Right? Would the k's be the same?
Yeah.
Yes. The only thing that's different is the distance. So how much spring energy does it have at point 1? It has 1 joule. How much spring energy does it have at point 4? Put a point 4 in there. 16 joules. So the 1 is the initial, the 16 is the final. So how do we find out how much work is done? The work done is the transfer of energy. What are we going to do, Marlon? We're going to subtract, exactly. Oops. We're going to subtract. The work required is 16 minus 1, 15 joules of energy.
So, final.
Say again, Ryan? Spring? Okay. Okay. I should note, you can't just substitute 0.3 in. Okay? Because the 0.3 represents delta X, not the total compression. If you put 0.3 in there, are you going to get 15? You're not. So watch out. Be careful. Star. Test. Exam. Be careful. Okay?
I'll get partial.
Well, of course you will. Here's the last sample.
Constant 23 vowels and 12 independent vowels.
Here's the last sample. No?
You get it right. Can you go back for 3 seconds? Just like just 3 seconds.
Hey Siri,
I'll never work for you.
you weren't on your phone.
You trying, Matthew?
I'm actually amazing at mimicking voices. I'll do next.
Shut up. It's not gonna work for you. She only reacts to
No, well,
because you got a coffee. I think I can copy. Hey Siri.
Okay, here's the sample. 5 kilogram mass, moving at 5 meters per second, strikes a spring bumper, having a spring constant of 15 meters per meter. So it's like a bumper that, like, when you run into it, it sort of slows you down, right? Well, like, or more like a bump. Think about like the bumpers on like the bumper cars. Find the kinetic energy of the mass before the collision. Find how far the spring will compress, and find the kinetic energy of the mass after compressing only 0.8 meters. You guys have the question, so I shouldn't have to wait. Find the kinetic energy of the mass before collision. So that's going to be EK equals mv squared over 2, or 1/2 mv squared. So the mass is 5. The velocity is also 5. 5 times 5 times 5 divided by 2. 62.5 joules.
But it's before the collision, so there's nothing like fancy that you have.
It's before the collision, right? All we're doing is finding the kinetic energy ahead of time.
How do you know that you don't need to have a work period?
Okay, so now, how far will the spring compress? All of that kinetic energy has to be transferred into spring energy, right? So EK 62.5 has to become US, right?
Oh my.
What?
Megan's pushing over the upside.
I hope you've got a bungee cord attached to you.
Oh.
No. She's pushing me.
Not very nice.
Not giving them time to even get the bunch of my phone.
So that kinetic energy, all of that 62.5, right? No, come on, think. This is the kinetic energy. All of that becomes US, right?
Let's be like my words.
All of this I've made it more complicated than it needs to be. The 62.5 becomes spring energy, so you put that 62.5 in for spring energy.
Think.
So that's
62.5, 1/2.
That's how I understand that.
Well, here I'm going to take half of 50, which is 25, and I got to divide by 25 to get it to the other side. Right? So 62.5 divided by 25 is 2.5, and then I got to take the square root.
Did you make these notes?
I did. These were made over from the old PowerPoint version, and I just never got around to actually, no. There probably was in one point when I did them in PowerPoint before I had a smartboard.
Okay, so I'm writing out why can't you do it in PowerPoint instead of there?
I can't write on them as easily in PowerPoint. It doesn't let you write as well. Okay, so that is the distance that the bumper will compress, right? So what if it only compresses 0.8? How fast is it going? How are you going to do that? Find the US for 0.8, right? E, I guess this would be ET really, right? The total energy is the kinetic energy plus the potential. That would be an S. The total is 62.5. We're solving for EK. 1/2 kx squared. What are we going to put in for x? 1.8. Yeah, that's the distance that it's being pushed there, right? Okay, so we're going to put that 0.8 there in. Figure that out. Half of 50 is 25 times 80 squared. Works out to be 16. And then just got to subtract, right?